Okay, Chemistry 3111. So where we left off last class was looking at chapter 12, but there was one reaction that I went over pretty quickly, and I wanted to review it with you before we move forward. And we were talking about the acidity of an alcohol. We took a look at the pKa of an alcohol. And so we said an alcohol like ethanol has a pKa of about 16. And we said the reason that sodium hydride is such an effective base at deprotonating an alcohol is because if you think of the alcohol as your acid, the hydride ion is your base. Okay, it's going to abstract the proton from the alcohol. You get an alkoxide, which in this case is sodium ethoxide. And then we get hydrogen gas, which is the conjugate acid. Now, if we compare the acid with the conjugate acid, you should remember that the equilibrium lies to the side of the weaker acid. Okay, if you took chemistry 3101 with me in the spring, you should especially remember that. I think I made students say it out loud. The equilibrium lies to the side of the weaker acid, and that's why our equilibrium arrow is pointing in this direction. We know the higher the pKa, the lower the acid. Now, again, sodium hydride is an excellent base for deprotonating alcohols, but it says here that sodium, potassium, and lithium metal, which are very reactive metals, are really good at deprotonating alcohols as well. Now, there's no mechanism provided for this reaction, so you don't have to worry about that. But if you take an alcohol like ethanol and you put it in the presence of sodium, just plain old sodium metal or potassium metal or lithium metal, what it's going to do is it's going to remove that proton to make your alkoxide. So this is sodium ethoxide here. And then the hydrogen that's liberated forms hydrogen gas. Okay. So here we say half H2. Why? Because it's a half a mole, right? If you have 1 to 1 to 1 of this, well, you can't have H2. You could only have one hydrogen, so you have to put a 1/2 in front of it. What's 1/2 times 2? It's 1, okay? So this is just a balanced reaction is all it is. Now, in case you don't remember, what does this arrow represent? Could anybody tell me what this arrow going up represents? Arrow pointing up to the sky, the skybound arrow. Does anybody know what that arrow going straight up is for? No? Okay, so the arrow that's pointing straight up, that means that the hydrogen that's liberated is a gas. Okay, it's a gas. And if it's a gas, then it's going to be forming, or it's going to form bubbles. And where do bubbles go? They go up out of the reaction. So they're going to go up out of the reaction. And so based on Le Chatelier's principle, if this is leaving the reaction flask as bubbles, right, that's going to push the reaction forward even more. Okay, so there you go. So that's one of the driving forces of both of these reactions is that you liberate hydrogen gas. And so it escapes the reaction mixture. And so it pushes the reaction forward. So again, if you need to review Le Chatelier's principle, it might be wise to do that. Very important principle in chemistry. So we talked about aereo, and we looked at this in detail last class, and we talked about how the pKa of an alcohol is usually somewhere between 15 and 18. We took a look at cyclohexanol versus phenol, and we said that phenol is much more acidic. It's 10 to the power of 8 times more acidic than cyclohexanol. It's not based off of atom, it's based off of resonance, because if we form the conjugate base of cyclohexanol, it has no resonance forms, but if we form the conjugate base of phenol, which is called phenoxide, it has all of these resonance forms here, and we know that that stabilizes the conjugate base, and so that explains why phenol is more acidic. Now, what if we were to compare ethanol and trichloroethanol? Now, this one can't be explained by atom, and it can't be explained by resonance, but we can explain that trichloroethanol is more acidic than ethanol because of induction, right? And I drew that here, sorry, my left hand at work here on the iPad, because you have the 3 chlorines, and those 3 chlorines have dipoles that are pulling in this direction, okay? And what they do is they stabilize the negative charge on the conjugate base, and that explains why trichloroethanol is more acidic than ethanol. Then we took a look at tert-butanol and ethanol. Now, this one's kind of tricky because it can't be explained using aereo at all. You can't use atom, you can't use resonance, you can't use induction, and you can't use orbital. If you draw the conjugate base of ethanol, you get ethoxide. If you draw the conjugate base of tert-butanol, you get tert-butoxide. Again, the negative charge is on an oxygen in both cases, so you can't use atom. There's no resonance structures for either of these conjugate bases. There's no inductive effects, and there's no difference in the orbital on which the negative charge is residing. And so we look at solvation effects in that case. And you know that tert-butoxide has all these methyl groups here, and so that makes the oxide more sterically hindered. And so what does that mean? It means that less solvent molecules are able to gather around and stabilize that negative charge. When we have ethoxide, we only have a tiny little ethyl group coming off of the oxygen, and so there's more room around it for solvent molecules to stabilize it. And so going back a slide, we call that a solvation effect. Okay, it's a solvation effect. So can we use aereo to solve everything in terms of pKa? No, the answer is absolutely not. And that's why if it's been a while since you took Organic Chemistry 1, it might be wise to go back and review pKa values, okay? It's very wise and borderline imperative that students memorize pKa values, the ones that are shown in the acids and bases chapter. Anyhow, so let's move on from there. And then after this, we talked about the preparation of, or we were starting to talk about the preparation of alcohols. So if what you're seeing on this slide looks familiar to you, it should, because it's review. We talked about the synthesis of alcohols in Organic Chemistry 1. Namely, we looked at these two reactions in Chapter 7. You remember that giant chapter about SN1, SN2, E1, and E2? Well, you see that SN2 is showing up and SN1 is showing up here. So those reactions are still pertinent in this class. Now let's take a look here, okay? What are we taking a look at? So the first reaction is showing you a primary alkyl halide. This is 1-chloropropane, right? Everybody should be able to name that compound, or you could call it propyl chloride. Either way, you're treating that with sodium hydroxide. Now, we know that propyl chloride is a really great electrophile. Why is that? Because we have a dipole between the carbon and the chlorine, and so we know that the carbon is delta positive. We know that the hydroxide has a full-on negative charge. Hydroxide is a strong base, but it's also a strong nucleophile, and we have a great electrophile, and it's a primary alkyl halide. And so what's going to happen will be an SN2 reaction, and you should be able to draw the curved arrows, the nucleophilic attack, and the loss of leaving group that occur to produce this alcohol. So why are we revisiting this reaction? It's because it's in the alcohols chapter, right? And we're forming an alcohol. Furthermore, if you take a tertiary alkyl halide, like this one that's shown here, you'd call this what? We'd call this 2-chloro-2-methylbutane. And that's a tertiary alkyl halide, so that's not going to undergo an SN2 reaction, but it can undergo an SN1 reaction. Now, there isn't enough room here to put the, well, maybe I could squeeze some of the mechanism, but who could tell me what the first step is going to be in the SN1 mechanism? Remember, SN2 is SN together. It's a concerted process, whereas SN1 is one at a time. So it's one step followed by a second step. Could anybody tell me what the first step is in an SN1 mechanism, in this mechanism? Oh, exactly. Thanks, Kristen. It's going to be a loss of leaving group, isn't it? Right? So Kristen says we're going to get a loss of leaving group. And so I'm going to draw the carbocation that's going to result. So we're going to end up with this carbocation, which is a tertiary carbocation. And so it's not going to rearrange. And so what's going to happen then is our water molecule is going to come in as our nucleophile. So we have our water molecule coming in like this. We get an oxonium ion produced from that. So we end up with our oxonium ion. Maybe I should draw the hydrogens. Well, I'll just draw it condensed like this, okay? And then I don't have a lot of space here. I'll just put proton transfer for the last step. You do a deprotonation with the chloride to get HCl. So you should be very, very familiar with these mechanisms, again, because they were covered in Chapter 7 of Organic Chemistry 1. Now, if you're wondering, where's the secondary alkyl halide? Why isn't that in here? Well, the reason why is because a secondary alkyl halide is not effective in an SN1 process because the loss of leaving group is too slow. You don't form a stable carbocation. And if you take a secondary alkyl halide and you treat it with a strong base, like sodium hydroxide, what's going to predominate will not be substitution to form an alcohol. It's going to be elimination, okay? So that's why a secondary alkyl halide is not shown on here. You're mostly going to get E2 in that case, okay? If you don't believe me, you could go back to that big table in Chapter 7 where it covers strong base, weak nucleophile, strong base, strong nucleophile, strong nucleophile, weak base, and then weak base, weak nucleophile. Then you look at primary, secondary, and tertiary, and you would see that if you take a secondary alkyl halide, you treat it with a strong base, strong nucleophile, what will predominate will be E2, okay? And that's not going to give you an alcohol, so that's why it's not on this slide. This chapter is about alcohols. All right, so based off of that, I said that we were going to tackle this question today. So we're taking cyclohexanol, and we're just treating it with sodium metal. Could anybody even describe to me, you don't have to name the compound, but could you describe the compound that's going to be formed? Could anybody tell me what's going to happen? You can use the most simplest terms to describe it. Doesn't have to be fancy. What would I get when I put cyclohexanol in sodium? So I'm just taking an alcohol and putting it, or reacting it with a metal, sodium metal. So what I'm going to get is an alkoxide in this case, right? I'm going to get an alkoxide. Hopefully you guys can hear me. So what I'm going to get is I'm going to end up with the alkoxide. So I have the negative charge on my oxygen. My sodium is going to be my counterion, and then I'm going to form half a mole of hydrogen gas. You can put H2 gas like that, that's totally fine. Or you can write an arrow going straight up like this to represent that this is a gas, okay, that is going up the smokestack, so to speak. What about the next one? We're taking, so this would be 2-butanol, and we're treating it with sodium hydride. What we're going to do in this case is I'm going to draw a little mechanism. So you should be able to draw sodium hydride, which is an ionic compound. You have the sodium cation, then you have the hydride anion. Remember, hydride, H minus, okay, is a really good base, but it is a terrible nucleophile. It's a terrible nucleophile because it's non-polarizable, but again, it's a very strong base. So because of that, what's going to happen is if I redraw my compound and I show the oxygen-hydrogen bond explicitly, there we go. What's going to happen is that my hydride ion is going to abstract my proton. So I get a proton transfer like this, and I form the alkoxide. So I end up with something that looks like this. There you go. There's an alkoxide. Sodium will be my counterion. But in this case, how many moles of hydrogen gas am I going to form? Well, in this case, it's not going to be a half a mole. It's going to be 1 mole, right? Because I've got 1 hydrogen plus 1 hydrogen. And so I end up with H2, okay? And I can just put an arrow going up like that. Everybody give me a thumbs up if you're with me on those reactions. Everybody with me on those two? Cha? All right, good. So remember, if you take an alcohol and put it in a metal, again, it could be sodium, it could be potassium or lithium, you're going to end up with an alkoxide. And if you take an alcohol and treat it with sodium hydride is a strong base. Okay, so that's going to deprotonate as well. You know, if you're wondering, what's the consequence of all this? What the heck am I supposed to do with this Mr. Dion? Well, remember, alkoxides are really good nucleophiles, right? So you could say, and I'll erase this in just a second, but you could take this alkoxide and treat it with something like ethyl iodide, and in that case, you'd make an ether, right? So it's a way to synthesize an ether. Anyhow, I'm getting ahead of the game here, so I'm going to erase this for now, but that's the idea, okay, as to why you might want to make an alkoxide. Now let's try something a little bit different. Sorry, this doesn't all squeeze on the, well, maybe it does squeeze on the slide here. What we're going to do now is we're going to take a look at this problem, which deals with pairs of alcohols, and we're going to identify the one that is more acidic. So we're just looking for the one that's more acidic, and then we're going to provide some kind of explanation. And so we might use Areo. You saw that we don't use Areo for everything, but we might use Areo in this case. I tell you what, why don't we start with B? Okay, we'll start with B. We've got this, what would you call this? 1, 2, 3, 4, 5. You'd call that 1, 2, 3, 4, 5 pentachlorophenol versus phenol. Could anybody tell me which one of those would be more acidic? Would it be the first one or the second one? Yeah, thanks, Erica. It's going to be the first one. So we'll say this one. I'll put a big circle around it, and I'm going to say more acidic because, could anybody answer why? Just give me a one-word answer. It doesn't have to be a one-word answer, but anybody have any? It's got something to do with a dipole. Yeah, you're right, Rachel. But how would you relate that to the concept of area? You're right. You're absolutely right. That you're looking at it and saying, yes, there's a dipole going this way. There's a dipole going this way. And there you go. The word is induction. Absolutely. But either way is fine. So more acidic because of induction. Great. Let's go ahead and try C. C is a little bit trickier. But if I take a look at C, could anybody tell me, would it be the first one or the second one? Would it be the first one or the second one in this case? This one's trickier. Yeah, it's going to be the second one. Thanks, Rachel. Absolutely. Now, the reason why, could you tell me, would it be atom, resonance, induction, or orbital? I'll give you a clue. It's one of those. Does anybody know which one it would be? It's resonance, isn't it? Yeah, absolutely. Okay. So if you're not sure about that, let me just draw the conjugate base. Okay. So I'll draw the conjugate base of the compound, which would look something like this. Okay. Now, at this point, I would expect you to understand all the different, or to be able to draw all the different resonance structures of a phenoxide like this. Okay. So there's nothing new with that one. That's the first one. But if we look at the second one, you see you've got this acetyl group. I know you guys have probably studied something like acetyl coenzyme A. This is called an acetyl or acetyl group on the end. And what happens is if you draw all the resonance forms, and I'm going to draw a few curved arrows here. So I'm going to put this pair of electrons over here, this pair over here, this pair here. And I'm going to show you that the negative charge can be delocalized up onto that second oxygen. So let me just draw it for you here. So we end up with something that looks like this. And then we have a double bond here, here, here. Then we have the negative charge on this oxygen. And of course, we have all the other resonance structures where the negative charge is on the ring, but I'm just skipping those ones for now. And so the answer is going to be, this one is going to be more acidic. And the answer why is resonance. Resonance. There we go. Thanks a lot, you guys. What about D? Which one? Would it be the first one or the second one is more acidic? Yep. Thanks, Rachel. Awesome. It's the second one. Rachel, why? Is it atom, resonance, induction, or orbital? Yep. It's resonance, right? This form has resonance forms. Resonance. Whereas the first one has no resonance forms, right? We saw the pK of phenol is about 10. One of my students said that his mnemonic was phenol. I mean, people have really interesting ways of remembering things because all alcohols end with all, but he said phenol, you get the OL, looks like the number 10, and the pK of phenol is about 10. I said, that's a very strange way of memorizing it, like I said, because all ethanol ends with OL, but anyhow, I don't know. People have all kinds of different ways of memorizing things. All right, so let's try A. I left A for last. Why? Could anybody tell me which one would be more acidic in this case? Would it be the first one or the second one? More acidic. Anybody have an idea? In this case, it's actually the first one. Okay, this one is more acidic. Where's my blue pen? More acidic. Okay, why is this one more acidic? It's based off of solvation. Okay, so solvation, right? This is a primary alcohol and this is a tertiary alcohol. So the primary alcohol, you're going to have more solvent molecules that can get around the conjugate base to stabilize it. But in the tertiary alcohol, less solvent molecules can get around to stabilize it. Does that make sense now that you see it? Right, the whole idea of solvation. It's new for this class. Yeah, it's something that we never talked about really in Organic Chemistry 1. All right, there we go. So pitter patter, let's move on from there. Again, if you think you're having deja vu, you're not. Everything on this slide is something that you've covered before. I'll prove it to you. It says alcohols can be synthesized from alkenes. In an addition reaction, we covered Markovnikov addition, acid catalyzed hydration in chapter 9. That's actually not true. We covered that more, I would say, in chapter 8. Okay, that's not correct. I'd say this one too. Oxymercuration, demercuration, we covered. These are all covered in chapter 8, aren't they? I don't know why it says section 9, but these are all covered in the alkenes chapter, right? So alkenes is chapter 8. And so we talked about Markovnikov addition, we talked about oxymercuration, demercuration, and we talked about the reason you would do that is to avoid carbocation, come on, rearrangements. And then we talked about anti-Markovnikov addition with hydroboration oxidation. So again, these two are Markovnikov addition. And then this last one here is anti-Markovnikov. So I know it says it at the bottom of the slide, but anyhow, there you go. So everybody, thumbs up if you remember those reactions. You can, Mr. Dion, I can't forget them, okay? I can't get them out of my head. Okay, cool. All right, so now that we've got that, you're like, hey, I like organic chemistry too. It's just a rehash of organic one. Hold on. We're going to get there in a second. Okay, so now we're getting into something a little more interesting. We're getting into some syntheses, and this is where you're going to have to reach back into the nether regions of your mind from organic one to see if you can solve these. So I'm going to walk through some of them with you, and I'm going to ask you some questions about some of them. Now, a reaction that doesn't come up a lot in organic one, I fully admit that, is solvolysis. So solvolysis, okay, which is an SN1 reaction. Okay, it's basically when you take a tertiary alkyl halide like this, you put it in a solvent, literally nothing more than a solvent like water, and then you end up with the alcohol. Okay, so this is something, like I said, it's not covered, or we didn't talk about it a ton in organic one, but it did come up in the class. Okay, so if you want to take a tertiary alkyl halide and convert it into a tertiary alcohol, well, we have bromine, which is a great leaving group, but a tertiary alkyl halide is too hindered for an SN2 reaction. And so what's our option? Our option is to put it in water. And so that way the bromine can leave, right? Like Kristen said, the first step in an SN1 is the loss of the leaving group. The water is going to come in and attack as a nucleophile. Then we do a proton transfer, and we get our tertiary alcohol. So again, if you need to go back and review it, this is called a solvolysis reaction. It's an SN1 mechanism. Now the next one, we're not starting with a tertiary alcohol. We're starting with, a tertiary alkyl bromide. We're starting with a primary alkyl bromide, and we want to make a primary alcohol. Now, is this going to be an SN1 or an SN2 process, do you think? And it's not a trick question. Yeah, absolutely. Thanks, Rachel. It's an SN2 process, isn't it? Yes, it's an SN2 process. Thanks, Erica. Great. So could anybody provide me with a reagent, even if you type it into the chat and it's not a complete structure? I'll figure it out. Does anybody have an idea what the reagent would be to convert the bromine into an OH group, a hydroxyl, an alcohol? This time we need a nucleophile, don't we, for an SN2? So in this case, it's going to be what? It's going to be a hydroxide, right? So we're going to need something like sodium hydroxide, right? Okay, so sodium hydroxide would be our reagent in that case. The next reaction, C, would this be so this one here, is this a Markovnikov or an anti-Markovnikov addition of water across that double bond? Is this Markovnikov or, thanks a lot, thanks Rachel, it's a Markovnikov addition. So Rachel, what's going to be or anybody, what's going to be my reaction conditions in this case? Anybody have an idea? It's a Markovnikov addition of water. Yeah, H3O plus, perfect, I love it. There we go, so let's scribble that down, H3O plus. The next one is an anti-Markovnikov addition. I'm sure you can recite this in your sleep. So the first step is going to be BH3THF. And the second step is going to be hydrogen peroxide, sodium hydroxide. And then the last one, I don't know if anybody took a look at these before class today, but this last one, is this a Markovnikov or anti-Markovnikov addition of water? It's a Markovnikov. Now in this case, you guys, I know you're all very astute. Can I use H3O plus in this specific case? Will it work? No, thanks, Rachel. Awesome. It's not going to work, is it? Okay. In this case, it won't work. If you're struggling and you can't figure out why, I'll show you. Thanks, Mustafa. I'll show you very quickly. Okay. And I know you probably know the answer. You probably don't need my help, but I'll just go over it with you quickly. in case it's been a while since you thought about this. So if you do the proton transfer in the first step, Markovnikov, right, the rich get richer, you would end up with this secondary carbocation. There's nothing wrong with a secondary carbocation. However, what you notice from this molecule is if we have a methyl shift, what's going to happen is you're going to end up, with a tertiary carbocation. And so you're going to get a rearrangement, and you can clearly see that there was no rearrangement here. So what's the answer? We have to use oxymercuration, demercuration. So I'll scribble that in. The first step is going to be mercury 2 acetate or mercuric acetate. Either one is fine. Water is going to be our solvent. And then in the second step, we use sodium borohydride for our demercuration step. And again, the reason we do this is to avoid carbocation rearrangement. There you go, pitter patter. Sounds good. All right. What do you think? Give me a thumbs up if you're with me on those reactions. I know what you're thinking. I love those reactions. I couldn't get enough of them in Organic 1, so I came back for more. Good. All right. You guys ready to tackle something new? Some new reactions? Out with the old, in with the new. I shouldn't say out with the old. I just mean in with some new reaction. Thanks, Anastasia. Good. Let's do it. Let's tackle some new stuff. So let's talk about reduction. Okay, so if you remember, what was the only kind of reduction we really looked at in Organic 1 would be if we took an alkene and we treated it with hydrogen gas and palladium, platinum, or nickel to make butane or something like that. That is a reduction. Okay, so in organic chemistry, if you add hydrogens, it's a reduction reaction. So what it's saying here is, obviously this is not an alcohol, that's just a plain old alkane, but what it's saying here is that there is another way to prepare alcohols, and it's by the reduction of a carbonyl. Okay, now if you don't remember what a carbonyl is, carbonyls are present in many functional groups. Carbonyls are present in ketones, aldehydes, carboxylic acids, esters, amides, etc., etc. So a carbonyl is really just the carbon with a double bond to oxygen, like that. Like I said, carbonyls are found in all kinds of different functional groups, but it's the reduction of a carbonyl. Now, another kind of aside that you might find a little bit annoying is that a lot of times, not a lot of times, if an organic chemist says, if they're talking, and they just say a carbonyl, a lot of times when we say a carbonyl, a lot of times we're only talking about aldehydes and ketones. So aldehydes and ketones. So again, I know it's a little bit annoying, but you've taken enough organic chemistry to know that we have strange ways of describing things sometimes. Now, you guys should remember from your chapter on like electrochemistry and when you looked at single displacement reactions in General Chemistry 1, that when you have an oxidation or a reduction reaction, that you have a change in oxidation state, right? Number one, I'd say that is key, is you have to remember that oxidation is losing electrons, reduction is gaining electrons. And so oxidation state is just a method of electron bookkeeping. That's all it is, okay? Now, oxidation states and formal charges are two very different ways of keeping track of electrons. I'm dead serious, okay? Because if you're thinking, well, I know how to do oxidation state from General Chemistry 1, and I know how to do formal charge, valence electrons, minus sticks, minus dots, but they are two different ways of keeping track of electrons, and I'll go over that with you. So let's take a look. It says here, to determine the oxidation state of an atom, imagine the electrons in the bond is a lone pair on the more electronegative atom. So what I'm getting at is this. Let's take a look at formal charge first, because this is near and dear to all of you. I know that all of you can calculate formal charge in your sleep. You don't need my help whatsoever. So if I was to give you a molecule like methanol, and I'm just going to redraw the molecule. I was going to. Anyhow, let me find it here. There we go. Okay, so when we're talking about formal charge, let me get my pen out here again. Talking about formal charge. Okay, if I draw a methanol molecule, which is this guy, it's the simplest possible alcohol, right? Methanol, okay? If I was to ask you what's the formal charge of this carbon, you would say, well, I've got 4 valence electrons minus 4 sticks and 0 dots, therefore it's 0. And you're absolutely right. When carbon has 4 bonds, it has no charge. But really what we're doing is we're dividing up all 4 of the bonds and we're breaking them homolytically. What that means is that each atom we're splitting the electrons evenly. So when we break this bond, the hydrogen gets 1 electron and then the carbon gets 1 electron. When we break this bond, the hydrogen gets 1, the carbon gets 1, et cetera, et cetera. And so when we're done, all of our homolytic cleavages, what do we have? We have a carbon that is surrounded by 4 electrons, and we can do the same old treatment. We'll say 4 valence electrons minus 0 sticks minus 4 dots gives you 0, right? So it's the same old thing. And so when we're calculating formal charge, even though you probably haven't realized it up until this point, what you're doing is you're breaking your bonds homolytically. Everybody gets an electron, right? You split them up equally. Now, when we're calculating oxidation state, it's something completely different, okay? So I'm going to use my green highlighter here. With oxidation state, what we're doing is we're breaking the bonds heterolytically. Now, hetero means one of the atoms is going to get the electrons and the other one doesn't. What's the answer? Well, you can see that in the notes up here. The electrons end up as a lone pair on the more electronegative atom. Now, I know you guys know carbon, nitrogen, oxygen, fluorine like this, chlorine, right, sulfur, phosphorus. So you don't need a lot, you don't need any guidance on, electronegativity increases going in this direction. And so if we think about our methanol molecule, if I redraw it for here, one of these days, Alice, where was I? Yep, if I redraw my methanol molecule here, okay. So now what we're going to do is we're going to break the bonds heterolytically. So let me ask you guys a question, and it's not a trick. What's more electronegative, a carbon or a hydrogen? Anybody? It's a carbon, right? So the carbon, all the carbon-hydrogen bonds, the carbon gets the 2 electrons from this bond, from this bond, and from this bond. Now, what about the bond between carbon and oxygen? Who's more electronegative? The answer is oxygen. So the oxygen gets the electrons in that case. So now you do the same darn old treatment you always do. You say 4 valence electrons minus 6 dots minus 0 sticks gives you -2. And so that tells you that the oxidation state of the carbon, so we'll put here oxidation state, is -2. Yes, the formal charge is 0. It has no formal charge, but its oxidation state is -2. All right, now, are you going to have to practice this? Of course, you're going to have to practice this. I'll show you another one. So this is the one we just did, is methanol, right here. Let's do the one that's way on the end, CO2, because we have enough room here. Now, if I finish up the Lewis structure of CO2, okay, there are no trick questions in this class. There's only 2 bonds. It's bonds between carbon and oxygen. Who's more electronegative, carbon or oxygen? The answer is oxygen. So if I draw the carbon and the oxygens, okay, the 4 electrons from these 2 bonds, those 4 electrons, where are they going to go? They're all going to go on the oxygen. So 1, 2, 3, 4. And the 4 electrons here, they're going to go on the oxygen. 1, 2, 3, 4. So now my carbon is naked. It's got nothing on it. So what am I going to say? I'm going to say 4 minus 0 dots minus 0 sticks gives me +4. So that's why the oxidation state of the carbon is +4. Give me a thumbs up if you're with me on that idea. Cha? Is everybody with me on the concept? Will you have to practice it? Absolutely. And you can be sure I'm going to ask you about oxidation states on the next quiz. Let's see here. We're going to get a chance to try some others, but you can see that we go from methane, which is -4, then we have methanol, which is -2, all the way up to formaldehyde, 0, +2, and +4. And so what's the bottom line? Why didn't you cover oxidation state of carbon in General Chemistry 1? It's because it can be -4, -3, -2, -1, 0, 1, 2, 3, 4. It can adopt all these different oxidation states, but now you know how to calculate it. So there you go. It took you what, a whole semester and a couple of days a day or 2 of lecturing, in organic chemistry 2 in order to figure out how to calculate the oxidation state of a carbon atom. So now what you need to remember is that oxidation is occurring when the number becomes more positive. Okay, so if the oxidation state is increasing, that's oxidation, right? Oxidation is losing electrons. Electrons are negative. If you lose negativity in your life, what do you become? More positive. So this would be oxidation. Oxidation is occurring in this direction. And then reduction is when the oxidation state, when the oxidation state is decreased. So we'll just draw an arrow going this direction, and we'll say this would be reduction. All right, so with all that in mind, what does that mean? What's our take-home message? Is if we take a carbonyl, okay, and a lot of times, like I said, when we're talking about a carbonyl, oftentimes we mean just aldehydes and ketones, and this is a ketone. Okay, we're reducing it to the alcohol. Now, I have a question for you guys, okay? You're going to need a piece of paper and a pencil. Can I give you a minute or maybe 30 seconds to see if you can calculate the oxidation state of this carbon, the one I have the little red arrow on? I'll put a timer on it since I have a hard time not talking. I'll give you 40 seconds. And if you finish that really quickly, see if you can calculate the oxidation state of this carbon, and we'll make sure that this is actually a reduction that's occurring. Oops, darn it, timer scared me. Okay, did anybody get an oxidation number for the carbon with the red arrow by it? Anybody get a number for that? And don't be shy, we're learning the subject. Anybody get a number for that one? Okay, all right, we're getting some different oxidation numbers here, so let's see if we can figure it out. Okay, so what we're going to do is I'm going to draw a new Lewis structure for this guy. There's not a lot of room here. So I'll just kind of zoom in. We've got a carbon, we've got a double bond to oxygen. Then we have a methyl group here and a methyl group down here. Now we know that oxygen is more electronegative than carbon. So I'm going to take the 4 electrons from the double bond, 1, 2, 3, 4. They're going to go on the oxygen. Now between the 2 carbons, they have the same electronegativity, so they're going to split the electrons. Okay, so one's going to, so again, they're the exact same. So one's going to get one and one's going to get the other. One's going to get one and one's going to get the other, right? It's not ionic at all. It's a totally covalent bond. And so what's the answer? The answer is going to be, I have 4 valence electrons minus 0 sticks minus 2 dots. That gives me positive 2. So this is positive 2. All right, and then if we look at the alcohol, I'll redraw a little Lewis structure for this guy here. Everybody needs a little Lewis in their life, right? So we'll put the hydrogen over here, CH3 down here, and CH3 down here. Okay, put in my lone pairs there. Okay, so we'll break the bond between the carbon and the oxygen first. The oxygen gets the lone pair. Between the carbon and the hydrogen, the carbon is going to get the lone pair because carbon is more electronegative. Now when we have a carbon-carbon bond, we're going to split it. So we're going to split both of those homolytically, or each one gets 1. So now the carbon is surrounded by 4 electrons. Put a circle around that. So I get 4 minus 0 sticks minus 4 dots gives me 0, like that. So the oxidation state here is going to be 0. So now if we take a look, we can see we're going from +2 to 0. So is this reduction? You bet your Bobby socks it is, right? We're going to a lower number, right? We're gaining electrons, right? If you remember oil rig, oxidation is losing. So if you remember this, oxidation is losing electrons, reduction is gaining electrons. Well, we gained 2 electrons because we went from something more positive to something more negative. All right, so the reducing agent is oxidized in the process and the carbonyl gets reduced. So reduction of a carbonyl group, what did we do in essence? I'm sure you all figured this out, is that if you look at the carbon and the oxygen in the carbonyl, one hydrogen went on the oxygen and the other one, I'll just pencil it in here, the other hydrogen went on the carbon. So everybody got a hydrogen, right? So in organic chemistry, you can think of reduction as being gaining electrons, but you can also think of it as gaining hydrogen atoms, okay? Either one is acceptable in this class. So how do you reduce a carbonyl? Well, there's actually 3 ways that we're going to look at it today. And the first one is a catalytic hydrogenation. You heard me mention this reaction earlier on today because we talked about taking an alkene and we said, okay, if you treat that with hydrogen gas and nickel, for example, you can make an alkane. Well, you can do a similar thing with the double bond between the carbon and the oxygen. What happens is you add one hydrogen to the oxygen, and then you add one hydrogen to this carbon, okay, which is not drawn because this is a bond line structure. And there you go, reduction. So if you're wondering what the heck is in this picture, Mr. D, what are those flasks and balloons? This is actually a picture of somebody doing some catalytic reductions here. And so if you're wondering why is the flask black, it's because the palladium, let me get a red pen here. The palladium, platinum, or nickel, it doesn't matter what it is, it's on carbon. So it's actually on charcoal. And so that's why it's got this black color to it. And in the balloon, this is actually a balloon with just hydrogen gas in it. And then there's a needle going down into the flask. So that puts a pressure, a positive pressure of hydrogen onto the reaction. And then you stir it around. And yeah, eventually the hydrogen adds to the carbonyl and you reduce. There's some other finer points in here which you would never be asked about. But if you're wondering, you know, what is this thing over here? This is a vacuum pump. So this is actually used to evacuate the flask. You hook it up with a hose and then you remove all the air and then you open up. There's a stopcock right here and you open that up and you allow the hydrogen gas to go in. And if you're wondering, if you're thinking, well, that just looks like a party balloon from the dollar store, you're right. That's all it is. Okay. It's one of the cheaper pieces of equipment you can get in the lab. The problem with this method, the problem with doing this is that it's not used a lot to reduce carbonyls. It's used a lot to do this because you can oftentimes do it at a low temperature. But if you're trying to do it at with a carbonyl, you have to have high temperature and high pressure. And so, you know, high temperature with hydrogen gas, I generally frown on that kind of thing. So yeah, so does it work? Yes. Is it great? Is it my first choice? No, probably not. Okay, but you still have to know it. All the organic chemists have to know it, okay? So what's the second method, right? I told you we're gonna go over 3 of them. This is the first one. The second one is using this reagent called sodium borohydride. So sodium borohydride is NaBH4, okay? If you draw a Lewis structure of sodium borohydride, you have the sodium cation, and then you have the BH4. Remember that boron only forms 3 bonds, so if it has 4 bonds, it's got a -1 charge. So sodium borohydride is a common reducing agent. And I just took a Google image of a bottle with some sodium borohydride. It's just a white solid. And it's what's cool about sodium borohydride is that you can just put a spatula in it and handle it in air and not worry about it a whole lot. It is hygroscopic, meaning it does absorb water from the atmosphere, but it's generally not a huge concern. And what's cool about this reaction is that you can do the reaction in 3 different solvents, either ethanol, methanol, or water. Okay, so any one of those solvents will work for the reduction using sodium borohydride. Now, if you were hoping to not learn any new mechanisms, well, I have some bad news. We're going to learn some new mechanisms. Okay, so we're going to actually take a look at the mechanism for this reaction. So I'm going to put a little star by this because you do have to know the mechanism for reduction of a carbonyl using sodium borohydride. However, if you read the textbook before coming to class today, you might have noticed that when it says, when it shows this mechanism, which is shown here on this slide, okay, it says that this mechanism is actually not that well understood. However, this is kind of a Sparks Notes version of a mechanism which is totally fine, okay? So remember, we have the borohydride ion that I drew in the previous slide, right? We have the sodium cation, and then we have the borohydride. Well, hydride by itself, H minus, right? Remember I told you earlier today that this is a crappy nucleophile. However, borohydride serves as an agent for delivery of the hydride ion. So you see, what we have in the first step is we have a nucleophilic attack, okay? So if I retrace the arrows in blue, we have a nucleophilic attack by one of the hydrides, okay, onto the carbonyl. Carbon cannot have 5 bonds, and so you have to break the pi bond and put the pair of electrons, and then we end up with an alkoxide. Now remember, you're doing this in a protic solvent. I said the solvent could be ethanol, methanol, or water. And so in this case, they're showing it in methanol, right? This is methanol right here. And so what happens in the last step is that alkoxide is hungry for an electron, so it just rips one off of the solvent And there you go. So you go from your, in this case, it shows it going from a ketone to an alcohol. And again, this is a mechanism that you should know. All right, not a well understood mechanism, but again, this mechanism will suffice. So some interesting points about the sodium borohydride reduction. What if you did the reduction of a carbonyl, okay, and remember that the carbon of the carbonyl is sp2 hybridized. Therefore, what's its molecular geometry, this carbon that I have the red arrow next to? Could anybody tell me what the molecular geometry of the carbon of the carbonyl is? Not a trick question, right? Thanks, Kristen. It's trigonal planar, isn't it? Right? It's trigonal planar. So what does that? I mean, Mr. Dion, trigonal planar. Well, if it's planar, what does that mean? It means it's flat. Okay, that's what it's trying to show here, is that this carbon is flat as a pancake because it's sp2 hybridized. So is the nucleophile, the hydride, going to discriminate between either face of the molecule? The answer is no. And so in that case, here you're forming one chiral center. So in this case, you'd end up with a pair of enantiomers. Okay, so these are enantiomers. And you'd end up with a racemic mixture. You'd get a 50-50 mixture of each of them. So again, it's not going to discriminate between either face of the molecule. So an unsymmetrical ketone is going to produce a pair of stereoisomers. Now, that was the second reducing agent. The third one is lithium aluminum hydride. And there are some points that I want to make about lithium aluminum hydride where my slides differ from the textbook a little bit. Okay, and I'll explain why. So it says here, the third one is lithium aluminum hydride. So if I draw the Lewis structure of lithium aluminum hydride, which we sometimes abbreviate LAH, like this, you can see somebody wrote LAH, that's lithium aluminum hydride. So we have our lithium cation, then we have aluminum attached to 1, 2, 3, 4 hydrogens. Now let's think about this. Aluminum has 3 valence electrons, minus 0 dots, minus 4 sticks. It's got a charge of -1, okay? So the aluminum hydride serves to deliver the hydride ion much the same way the borohydride did. We get an alkoxide and then we protonate that. But notice that this is not a one-step process. Look, if we go back here, everything here is all mixed together, the sodium borohydride and the methanol. This is not a two-step reaction. But with lithium aluminum hydride reduction, lithium aluminum hydride will actually cause a fire if you put it in water. You can see here it's contained in this can. Okay, why? Because it can cause a fire. Okay, so it's very dangerous, lithium aluminum hydride. And so it's a two-step process. The first step is lithium aluminum hydride, again abbreviated LAH. And the second step, I put water here. Okay, what you're going to see in the edition of the textbook we're on now is he puts H3O plus. Okay, and he goes into a little explanation on this, is that anytime you see an alkoxide like this, and you want to protonate it to form an alcohol, in the old versions of the textbook, in the first editions, he always put water as the acid that would protonate it, okay? But in the new edition, what you guys have, okay, online, he always puts H3O plus. And so since in the past, I've had students that use the old version of the textbook, they said, I want a hard copy. I said, well, what he had in the original textbook isn't wrong. There's nothing wrong with it. It's just that aqueous acid is probably a better choice, okay? So I will accept either one for the second step. So again, if you're trying to protonate an alkoxide for Mr. Dion, you could write water, I'll give it 100%, or you could put H3O plus. Either one is perfectly correct, okay? They're both perfectly fine. So you probably noticed that there's this real similarity between the sodium borohydride, which is shown here, and the lithium aluminum hydride, which is shown here, right? They both have an element, boron or aluminum, that has 3 valence electrons with 4 hydrogens. They both have a cation, which is a group 1 metal. But it turns out that lithium aluminum hydride, like I said, is a lot more reactive than sodium borohydride. Now, I don't go into all the details as to why that is, but one of them has to do with the cation, lithium versus sodium. And it turns out that lithium is a stronger Lewis acid than sodium, and that renders the carbonyl more electrophilic. And I'm not going to go into the details on that because it's beyond the scope of our course, but if you want to look into it, you could. But I'd say the bottom line is what I put in bold here is that lithium aluminum hydride is much more reactive than sodium borohydride. So what you're going to see in a second is if we draw a line down the middle here, is that sodium borohydride can be used to reduce aldehydes. It can be used to reduce ketones, whereas lithium aluminum hydride, I'll just copy it, paste this over here. It can be used to reduce aldehydes, ketones, esters, and carboxylic acids. It can be used to reduce all of those. And it has other utilities as well. But for this class, this chapter, this is what we're going to see. All right. So with that in mind, let's take a look at the mechanism of lithium aluminum hydride reduction. So it says here, LAH, lithium aluminum hydride, is much more reactive and cannot be used in the presence of a product solvent like water. So therefore, you do it in 2 steps. In step 1, you put in the lithium aluminum hydride. In step 2, you put in water. And again, it can be water or hydronium, which is just aqueous acid. Either one is totally fine. So let's take a look at the mechanism. And this is a mechanism I expect you to know. If you're looking at it and saying, well, this looks pretty darn similar, all I'd have to do is put a boron in here and it would be the same thing as what we saw before. You're right. It is essentially identical, okay? The aluminum hydride serves as a delivery agent. For the hydride ion, you form an alkoxide. So this is your alkoxide here. And then you do a proton transfer with either water or aqueous acid. Here they've shown H3O+, and you protonate and you're done. That's it, my friends. So as far as, I don't like to make too harsh judgments because everybody's different in their learning styles. But I'd say, based off of some of the mechanisms that we've learned in this class, I'd say that these 2 mechanisms, the reduction with sodium borohydride and lithium aluminum hydride, not as bad as some, or not as tough as some of the other mechanisms that we learned. Now, before we move on to section 12.5, I do have a couple more points that I need to cover in 12.4. If you're very astute, and I know you all are, you probably figured this out already, that let's say you had this compound, okay? It's a beautiful compound. You have a 7-membered ring. You have a ketone in it, and you have an alkene, right? Does everybody see that? You've got a carbonyl, and you've got an alkene. So I told you that you can reduce a carbonyl with hydrogen gas and palladium, platinum, or nickel. But if you were to take this compound and treat it with H2 gas, what are you going to do? You're going to reduce the double bond and you're going to reduce the carbonyl. So it's not selective. However, if you reduce it using sodium borohydride or lithium aluminum hydride, those are going to be selective for only reducing the carbonyl, and the alkene is going to remain intact. Okay, so hopefully that gives you a little bit of an insight. So I'm going to put here or H3O+, as to why a good organic chemist, she or he has to know so many reactions. Maybe there's a scenario where you need to reduce both the carbonyl and the alkene. So you would use hydrogen gas. Maybe there's a scenario where you just need to reduce the carbonyl. I'm not sure. Is there a typo on those percentages? I wouldn't say so. So what it's saying is this reaction is going to work in a 90 to 95% yield. So it's a really good reaction, works very well. And it's saying that these 2 reactions work also in a 99. There you go. So they both work. So these are 2 different reactions, right? These are 2 different things that are happening. Okay, there you go. So one is selective for just the carbonyl, pretty useful, no worries. And the other one is not selective. It's just going to reduce everything. So yeah, there we go. All right, now some interesting points about organic chemistry. I know we're all just learning the subject, right? It's your second class in organic chemistry, but you can imagine that you guys know that money makes the world go around, right? Everybody wants to make as much money as they can, and organic chemists are just like everybody else. And so when it comes to reducing agents, my friends, there are so many. So the only ones that we've covered today are hydrogen gas, which you already knew, and then sodium borohydride, and lithium aluminum hydride, right? That's been our focus for the past, 20 minutes or something. I'm going to tell you right now that there are so many variations on these 2 reagents. Everybody and their dog gets in on these, and they come up with new reagents where they just change the R groups. They make the R group maybe an alkoxide, or right, like OR group, or they could make a cyano group, or, you know, a cyano group, or they could make some big bulky groups like a tert-butyl group or something like that. But the bottom line is you can change the R groups that are highlighted in green to all kinds of different R groups. And what that does is it just changes the reactivity. You see that he uses the words fine-tuned, okay? So very specified for very special scenarios. And so if you go and try to shop on it from a chemical supplier for some kind of reducing agent, I'm not kidding, there are literally hundreds of them out there, okay? Now, there's only one other one that we really see in this class, and it's at the very end of the class. I mean, in like the second to last week or something. We look at this one here. It's called NaBH3CN. So you just replace one of the hydrogens with a cyano group. This is called sodium cyanoborohydride. Borohydride. And it has some special reactivity when we look at the reduction, or when we look at some reductions later on in the class. Again, you don't need to know it for this chapter, but I'm just putting the bug in your ear that we are going to take a look at one more later on, but that's much later on. So don't worry about it now. Another thing I told you is that lithium aluminum hydride is very powerful. It is a very strong reducing agent. So I said it can reduce aldehydes and ketones, but I said it can also, I said LAH can also reduce esters and carboxylic acids, okay? Whereas sodium borohydride can't reduce a carboxylic acid and an ester. Now, again, the first step is LAH. The second step, here it says H2O. I'm going to put here for both of them, or H3O plus, or H3O plus. Either one is perfectly acceptable. But what you notice here, what's the difference between these two reductions and the reduction of a ketone or aldehyde is this. It's excess, isn't it? Right here we need excess, and here we need excess. The reason why is you need more than one equivalent. Now, this mechanism here is not covered in this chapter. We're going to take a look at it later on when we get to the carboxylic acids chapter. But this mechanism is covered, okay? And what you notice is that the methoxy group ends up coming off as an alcohol. And I am going to show you that mechanism. So let's take a look here. So I know it's kind of small, but I'll zoom in just a second. Reduction of an ester requires two equivalents of the hydride. So two equivalents. That's why we need excess. Okay, you need more than one equivalent. The first two steps result in the formation of an aldehyde, but what do you know? You know that when you have an aldehyde in the presence of LAH, it gets reduced to an alcohol. So let's take a look at the mechanism. So bear with me as I zoom in here. Okay, here's step one. You have your ester. All right, good. You have your lithium aluminum hydride ion. Okay, great. So we have a carbonyl, which has a strong dipole. So we have a good electrophile, we have a nucleophile, and so we have our nucleophilic attack. We have the breakage of our pi bond to form an alkoxide. Now this intermediate here is really interesting, okay? It's what we call a tetrahedral intermediate because this carbon is tetrahedral. It went from being sp2 hybridized to being sp3 hybridized. So we call it, again, a tetrahedral intermediate. And what happens is you lose methoxide, right? You see you reform the pi bond and you lose the methoxide. And I'm going to get back to that in just a second. Where was I? Okay, so you lose methoxide and then you form an aldehyde, right? Because you reform the double bond here, and that's the double bond here of an aldehyde. Now, we know that when you have an aldehyde, it just gets reduced, right? First, you deliver the hydride, form an alkoxide, then H3O plus comes in, you do a proton transfer. So the one kind of like what moment in this mechanism is this part here, loss of a leaving group. It says here, loss of an alkoxide. You're losing, let me use a finer tipped pen here. You're losing methoxide. So losing methoxide. I put negative next to it. Is methoxide, let me ask you a question, and I'm not trying to fool you. Is methoxide a good leaving group? Well, you can probably see it on the slide, okay? It says here, methoxide is not a good leaving group. It's a terrible leaving group. Then why the heck would this even happen? Okay, methoxide's not a good leaving group. It's the conjugate base of an alcohol, which is a weak acid. So why would that happen? The reason it happens, the reason that this step can happen is because the driving force is that you form an aldehyde in the end, which is more stable than the tetrahedral intermediate. Okay, so that's why the methoxide leaves. Again, it might be kind of like, why would that happen? Well, again, it's because the high energy intermediate, the alkoxide, becomes a more stable aldehyde. Okay, so let me write this down here. High energy intermediate, that's the alkoxide, becomes something more stable, which is an aldehyde. Again, kind of weird, but there's all kinds of interesting things that happen in organic chemistry, as you know. And so there we go. All right, so what I'm going to do now is I want to take a short break, and there's two questions here that I would like you to try. Okay, so I want you to get a pencil and paper out and try these. The first one is an aldehyde, and I want you to try to draw the product and a mechanism. So get a pencil and pen out. And for the second step, you can use water. I'm going to use hydronium since that's what he likes to use in the mechanisms in the book. And then the second one is going to be the reduction of the carbonyl using sodium borohydride, and then methanol is in there as well as our solvent. I'm pretty sure that all of you can draw the alcohol in a split second without any of my help, but I want you to take the time to draw the mechanism. Like I always say, can you learn organic chemistry just by watching somebody do it? I'd say that's impossible, right? You got to give it the old college try. So we'll take a break, and then we'll come back and we'll tackle these. So just come on. There we go. Just bear with me. There we go. All right.